In this video, we are going to break down connecting to an Ethernet LAN. Connecting to an Ethernet LAN is relatively straightforward, but before we get into the understanding what all that is, we need to understand the parts to actually getting it done so that we understand you have a computer, you have a switch, how do you make them talk to each other? Connection media and the connection requirements for an Ethernet LAN, functions of the network interface card in an Ethernet LAN, various Ethernet implementations and the associated specifications, straight through and crossover twisted pair cables, standards of running Ethernet over unshielded twisted pair. We'll also take a look at Rj45 used in Ethernet UTP installations, wiring standards and uses for straight through Ethernet cables, wiring standards and uses for crossover Ethernet cables, compare straight through and crossover Ethernet cables, and fiber as a connection media. We'll also take a look at how fiber optic cables are constructed, multi-mode and single-mode fiber, the function and specifications for optical transmitters, the various connector types used to terminate fiber optic cables, how to maintain fiber optic connectors, and dense wavelength division multiplexing. It's a mouthful, but basically it's how you get traffic over fiber. So Ethernet on layer 1. The mechanical properties of Ethernet depend on the type of physical media. So there is coax, copper, and fiber. Now coax, or coaxial as it's broken down, isn't typically used anymore. I haven't personally ever seen it in a regular network, but it is how my cable connection comes into my house. So there's a cable that plugs into my modem, and then from my modem it's a handoff to Ethernet to my router. And that's how I get everything working. So there's that comes into play. Ethernet was originally based on the idea of computers communicating over a shared coaxial cable, sharing files and applications. That style of deployment was typically referred as thicknet, and it's a little dated, early 2000s, late 90s, that type of style. At least that's, I've never personally seen it, so that's, based off what I've been told and people that have experienced it, that's what they said. And typically they would use what they call a vampire tap, which I believe was just something that they would screw into another cable, and then they would just be acting as a way to bridge the connection between the actual main trunk cable and a leaf cable that was needed to be using that particular cable. Now Ethernet layer 1, what you see on your screen on the left hand side is an example of Ethernet cabling. So you have the shielded twisted pair right here. So this is the external shielding. Actually, let me grab my pen pad real quick. So you've got your shielding here, and this shielding is going to be the thing that you see the most of. So you've got, that's weird. That was odd. Oh, that's really weird. Having some technical issues with my pen, so I won't worry about that. My actual pen itself, I can still draw with it. The irony of it. So right now you have this right here. This guy right here is the actual shielded twisted pair. I'm sorry, the unshielded twisted pair. You have that. Then you have these little individual wires that are coming out here, and each one is twisted in a unique manner to each other. And so the way that you would look at this is normally you'd have orange stripe, orange. You'd have blue stripe. I'm sorry, blue stripe, blue. You have green stripe, green, you have brown stripe, brown. Now what you normally would do with this is you'd have an Rj45 Jack that would look something like this, and it's going to have a little tab on the top of it so that it can plug into the Ethernet port on the switch. And then if you were to flip this guy over, you're going to have a bunch of little pins sitting inside of here, and that each one of these wires here would be slid inside of a little pre-drilled hole here on this guy. You'd slide this guy in, make sure that you have cut enough of this back right here, the actual shielding, to expose the individual wires. You would trim the wires to the correct length so that basically this wire right here would come to about here. The blue line is inside of the jack, and these wires would get pushed all the way up through here. And then you take a punch down tool and you would crimp the wire. So what you would do is there's these little brass tabs that are inside of this guy right here. And what you would actually be doing is you'd be pressing these brass tabs inside of the cable of this little wire here. And then that's how the connection would be made. And then you go from there. And that's how you would go about doing that. On the other side over here, you've got different types of fiber. And depending on what you're needing, that's going to be how it would work out. This right here is going to be an example of stick and click. This one down here is stick and twist because you see a little adapter piece right there that it's got. Over here, this is typically going to be the style. If you have a fiber patch panel at the top of your rack, you're typically going to run plug this side here into the fiber patch panel, and then the other end of that connection, which it could be this guy or it could be this guy. It really depends. I normally only see this style right here in the enterprise world, and then you would stick that end into the SFP module on your router, your switch, or what have you, and that's how you would get the fiber connectivity between the two. Now, when it comes to network interface cards, this is connects the computer to the network. So it's going to plug into the motherboard and provides a port for connecting to the network PCs. To the network PCs. So unique MAC address is burned into onto each NIC, and the NIC is a device working on layer 1, which is the physical layer, and layer 2, which is the data link layer. Now, when it comes to Ethernet media, you have quite a few different breakdowns for this. You've got everything from here. You've got 100 base TX, and then you've got 1,000 base T. So if you have category 5E, which is what these two basically are, 5 was dedicated just to 100 megabits. Category 5E allowed you to go up to gigabit, and that utilized all 8 wires, all 4 pair. And then all the ones below here, this 1000 base SX, this is going to be your SX. You're going to have like basically like a standard range. You're going to have a long range, and you're going to have like they don't really specify this. Like LR would be like an extended long range because of it's just its distance here. So different capabilities out there, as you can see. Now, when it comes down to understanding, you have this T, you have this X, things like that. These are broken down into different terms. So it's important to understand what they mean. So the first letter of this type of wire is T, means twisted pair. S means short range multi-mode optical cable. L means long range single mode or multi-mode cable. Typically, what you're going to see in long range, you're going to see single mode. And inside of the data center, inside of your closets, inside of your racking, you're going to see multi-mode fiber. E means extended range. Z means long range single mode cable at a higher wavelength. So just be aware of those when you're moving forward. Now, Ethernet media, the second letter, X means a 4B or 5B block coding for fast Ethernet, or an 8B or 10B block coding for gigabit Ethernet. R means 64B or 66B block coding. Those are just the way that it's transcoded on the wire so that the other end of the connection knows what to listen for. Now, copper Ethernet, a UTP cable is a 4-pair wire. Each of the 8 individual copper wires is in a UTP cable is covered by insulating material, as you saw in that picture that I showed you. Now, when it comes to the different categories, I'm starting to show off a category 5 and work our way from there. There are older categories, like category 3 and category 1, things like that. Those are so old and not used anymore. I didn't really see the validity in showing them to you, but there are older versions. If you'd like to know what they are, feel free to Google the category 3, category 2, category 1 Ethernet. There's plenty of resources out there for you. The category 5 is transmission speeds of up to 100 megabits per second. Category 5E allowed you to use 1000 megabits per second. By doing this, category 5 utilized 4 of the 8 wires, or 2 pair. Category 5E utilizes all 8 wires. Category 6 is 4 24-gauge wires, which can transmit up to speeds of 1 gigabit per second. And Cat 6A can support up to 10 gigabits per second. So very, very quick, very, very fast for the internal network. Now, some of the media requirements are pretty unique. So, for instance, you have the 10 base T, which is data, and there are category 3, 4, 5, etc. UTP 2 pair. Then you have 1000 or 100 base TX, and this was the you would use 2 pairs to get to 100 megs. You would use 4 pair or all 8 wires to get to a gigabit, Cat5, Cat5e, and then anything above that you could use. Technically, this is a little incorrect because you can't use Cat5e to go anything faster than gigabit, so you'd have to go Cat6. But these are some of the ranges. The maximum segment length is accurate though. Now the Rj45 connector, if you've never seen one, there you go. Now the guy on the left here, the guy on the left is going to be the actual Rj45 jack that I just described a minute or two ago. And this guy right here, if you see these little 8 metal tabs here, and what you're going to do is you're going to take and you're going to punch these guys down. So if you were to look at this and if you were to spin it around, so the idea here is when you're looking at it with the tab down facing the floor and this guy facing the ceiling, this is how you'd want to look at it. So you'd want to go orange stripe orange, green stripe blue, blue stripe green, brown stripe brown. That'd be the how I would do it, and what that's going to allow you to do is have what they call a straight through cable. If you do that on both ends, you're going to be good to go. Now obviously you see the green hue in the background here, and that's going to be the cable coming in here and getting punched down into the jack. Now the guy on the right over here, this is going to be the wall jack drop that you deal with. So this guy right here is going to be what you plug into the wall, and this guy right here is going to plug into here. And the way this is going to map out is you have this guy right here. Let me grab my pen tool real quick. You're going to take and let me switch colors to something a bit more specific. Let me grab red. So, and make my size just a little bit bigger. So you're going to take all right, that's just weird. So what's going to end up happening is, just to give you guys an idea, this guy right here, this side right here would get plugged into on this side over here. This side would get plugged into right here. This pin right here would get pinned into this guy right there, and then they would just all follow suit from there. The tab right here is down here at the bottom. This would get plugged in right here. Now, that being said, you also have these little things down at the bottom. That's really hard to see, isn't it? I think I might have to restart my computer. I'm having issues. So what you see here, these 8 wires are going to connect down to the computer and whatnot, maybe an IP phone. Now here at the bottom, I know you guys can't really see it too well, but if you're seeing at the bottom here, these little feet on the bottom of this jack, they're different colors here. And each color on this tab indicates a wire here. Now this is from on this side would go back to the patch panel on the in your switch closet, and what you would do is you'd run a cable from the patch panel to this jack right here, and then what you would do is you take the 8 wires and each one of them would get punched down into this guy right like so. There's a punch down tool that you would use. You would lay the cable across. There's like a little valley, if you will. So the idea here is this little tab is built more like this, right? And so you would lay the wire through here like that, and then you would take the punch down tool, punch it down, and then what will end up happening is this extra cable right here would actually get clipped off, and then this wire would sit in between these 2 metal tabs, and that's what would provide connectivity to this guy. You do that for 8 wires, you're good to go, the connection goes back. And so then that's how you would go about doing that. That 100-meter thing that they were talking about earlier, that is from the network adapter of the computer to the network adapter of the switch. So the connection from, say, the switch that's sitting inside your rack to the patch panel, which is typically right below it, the patch panel out to this guy here to this, and then from here out to the computer, this entire length should be 100 meters or less. If it's going to be longer than that, you need to throw another box in somewhere in the path to be able to get your connectivity from point A to point B. Now, straight through Ethernet cables are pretty straightforward for the most part. The way this is going to work out is you have your different pinouts. So you're going to be using pins 1, 2, 3, and 6. So you're going to have a transmit, a receive, and a receive. You're going to have green stripe, green, or I'm sorry, white, green stripe, then you're going to have green, orange stripe, orange. This is for your 10 base T and your 100 base T. So again, that's how you're going to set it up. Now over here for gigabit, if you wanted to run gigabit, you'd have to go in here and set it up in such a way. Now this is going to be, you would see this where you'd go green stripe green, orange stripe blue, blue stripe orange, brown stripe brown. Now, in my experience of doing cabling, and I've done quite a bit of it at my time, typically the way that I would cable out is I would do, let me grab my pen real quick. I've always done it orange stripe, orange, green stripe, green, or blue, blue stripe, green, brown stripe, brown. That's how I've always done it. I've never had a problem. Now, as long as both ends match on the cable, so this side right here matches the remote end, so the other end of the cable, that's what they call a straight through cable, because the both ends of the connection are the same. This also falls back to the EIA, TIA, 568B standard. And what that means is this EIA is the standard, EIA, TIA is a standard, 568 is the specification. So the way this works out for you and I is this is how I would go about cabling something out if I was to do it. That's actually how I've always done my cabling, and I've never had a problem with it. It's always comes up as 100 megabits per second or gigabit or what have you. That's just how I go ahead and do it. In my experience, it works just the same. Now, when it comes to crossover, it's a little bit different. Crossover cable, you have a 568B and you have 568A. Now, the difference between these two is the pinout. Okay, so you'll see here that crossover cables connect like devices, where straight through cables connect not like devices. We'll talk about actually that in the next slide. But if you look right here, if you look, you'll have pin 1, 2, 3, and 6. You're actually going to flip them around a little bit because the transmit needs to be the receive needs to be the transmit. So that's the thing with crossover. You're trying to send traffic out and it needs to be received on the other end, and vice versa. So for gigabit here, you would need to go pin 1 to pin 3, pin 2 to pin 6, pin 3 to pin 1, pin 4 to 7, 5 to 8, 6 to 2, 7 to 4, 8 to 5. So that's going to be your pinouts as you need them to be. So that's going to be how you would look at it. You can use this for reference. I do all the time because I can never remember the crossover cable pinout, so I usually look it up when I need to know. Now, straight through versus crossover. Straight through cables are for the following cabling. You're going to do switch to router, switch to PC, or server. So this is going to be non-light devices. So you're going to be going from a computer to a switch. If the switch is in the middle somewhere, then you can use Ethernet all day long. The moment you're going to be connecting like devices together, you need to be using crossover cables because the send and receive pins need to be swapped as you're going across. So switch to switch, router to router, router to port, router Ethernet port to PC NIC, PC to PC. That's basically how it goes. Now, Ethernet fiber connection. Optical fiber is a flexible, transparent fiber made of very pure glass. So that's typically how I've seen it. I know plastic is also out there. I hear that glass has better transmission capabilities. I haven't seen any difference, to be honest with you, but that's just what I've heard. So I've deployed a lot of fiber in the data center and inside of campus LANs. It's really no different than when you do it in a service provider. It's just you're dealing with higher bandwidths because of the fact that you're dealing with more connectivity. It's widely used in fiber optic communication, which permits transmission over longer distances and at higher bandwidths. That's really what fiber's game is. You're going longer distances and you need faster speeds. That's what fiber's basically for. Light should be reflected in such a way to stay inside the optical fiber. So that's really, really important. So refraction is basically light leaks out of the fiber core, and that's really not good because then technically what you're doing is you're losing forwarding. So you're dropping packets essentially. Even though it's layer 1, you're still dropping bits, or your light waves are not getting across the wire to where they need to be. Reflection is light remains inside of the fiber core. That's really good. So if you're having a problem with, whether it's dirty endpoints, maybe you've got maybe your fiber cable has been spliced somehow, and it's leaking light. I personally have never seen that happen, but I'm sure it could. It'd be like if I've had a situation a long time ago when I first got into IT. I was called out to a customer's school, and or was I? No, I'm sorry. I was working for the school. I was for a help desk job, I think it was. And what ended up happening was my boss, who was the network admin, he sent me to one of these schools, and he said, second floor of the school is going to be in a utility closet out at the top near the ceiling. I was like, okay. So I got there, and in the same room there was this wash basin style thing where they have the mop bucket, and then you'd fill the mop bucket with hot water, and you'd be able to go mop. Well, the problem was this switch has been sitting in this closet for a few years. It's just been sitting there doing its thing. Well, the problem was that all the moisture inside of the room when people would go, the maintenance team would come in there and start mopping it at night. The moisture actually had corroded the Ethernet, or I'm sorry, the copper connections on the switch and the Ethernet cables, and we were noticing a lot of packet loss. And so I was sent there, and it's like, well, I asked him, I said, how do I troubleshoot that? I've never dealt with that before. And he goes, you know what? He's like, check the Ethernet connections. He's like, because the switch wasn't overheating, the switch wasn't, he had done a couple of, you can do diagnostics on different platforms of Cisco switches. 2960 on gigabit. I think it's all gigabit. As far as that's all I can think of is gigabit. You can do a cable test, and what that cable test is going to allow you to do is it's going to test all four pairs, all 8 wires, from start to finish. And he was actually getting loss and opens, I think is what the other one was, and what that was indicating to him was a layer 1 problem. And so I went there, and sure enough, when I unclipped the wire and I had him on the phone, and I said, yeah, this thing is like corroded bad. And so what he ended up having me do is we narrowed it down. It was the patch panel to the switch, so it wasn't anything really crazy. I didn't have to re-end a bunch of cables. So I went in there and I just went to the data center. I pulled out a handful of cables and swapped them out. Problem solved. But that's an indication Ethernet-wise with corrosion at the copper connections. I've also had to deal with people unplugging a fiber module, like they physically take the fiber cable out of the SFP module, and they lay it on top of the device. And then, they leave it out. It's a dusty area, dust gets inside there, and all of a sudden we're noticing there's issues and packet loss. And so I've had to go in and clean those up a few times. And, a lot of times, if you're not sure, we just swap it out with a new one, and it eliminates the problem. But that does happen every now and again. Now, fiber optic materials are pretty straightforward, similar in fashion to the way that Ethernet works. So the first thing you're going to deal with is the fiber core and cladding are made of silica, which basically is like silica sand. It turns into glass, that type of stuff. Light is confined in the core because of the properties of glass. The properties are controlled by selectively adding various elements, and typically what you're doing is there's inside the copper you're dealing with these dopant particles, which helps keep the particles in play, and it reflects instead of refracts. And the buffer or coating is usually plastic to protect the fiber. So you're going to have it running inside of a piece of plastic that's going to protect it from the outside elements. Now, fiber types, the first one you're going to have is the one you're going to see when you work in short range style setups. You're going to have multi-mode fiber. 50 microns for step index, 62.5 microns for graded index, cladding diameter is 125 microns, bit rate distance is more than 500 megahertz per kilometer. So basically it allows many paths or modes for the light or LED transmitter. So this allows you to do it gives you a lot of flexibility inside the data center. So that's where you're typically going to see this at short range. And you're going to have single mode fiber. Now, single mode fiber is typically going to be done for the longer ranges. And higher bit rate, you can see there's 100 terahertz per kilometer, which is much, much higher. And allows only for a single path for the light or laser transmitter. So again, it's going to be not as useful in the data center because of the fact that you're trying to transmit multiple streams of light instead of a single stream of light with single mode. Now, optical transmitters turn electrical current into light. Now, common light sources are fiber communications, are LEDs and lasers. Now, there's this thing known as a media converter. And what the media converter is, and to give you guys an idea of how this works, if you were to see a downtown building, you see this really tall building, maybe 30, 40 stories high. In between these floors, you typically have fiber riser runs, and this is how you get the provider is going to drop off the demarc, and from there the fiber runs are going to run up to the suites and to the network gear of the individual offices. Well, in this case here, the same thing happens. So you have a media converter that takes and converts that fiber into an electrical signal and vice versa. So if you have, let's say for instance, I've worked in for many companies as a consultant where we walk in and we have, on the 5th floor is where their data center sits, and the 2nd floor is where their Ethernet handoff comes in for the provider. So we need to be able to get them internet connectivity at the 5th floor. Well, they bought a 100 meg circuit, so we need to make sure that we have at least 100 meg connectivity between the 2 floors. So we get a media converter capable of converting to 100 megs. So we plug in the Ethernet cable into the media converter, that flips it over to fiber up to the 5th floor. We go to the 5th floor, we terminate the other end of the fiber into that media converter, and then from there it goes media converter to Ethernet to whatever device they have plugged in. So it turns electrical current into light. So it's very, very handy in that regard. Now, fiber connection types, there's about 70 of them out there. So there's way more than I can just, break down here. They come in threaded, bayonet, and push-pull. They have metal or plastic sleeves, and they usually have simplex connectors. They have ST for stick and twist. They have SC, which is typically going to be stick and click. And then they have FC, which is going to be for telco, which I believe is flex and click, but I could be wrong on that one. That's typically for telco equipment. But those are the general breakdowns to how they break out. Fiber connection maintenance. Dust particles can be 20 microns or larger. So just 1 micron dust particle landing on the core can cause up to 1 decibel of loss, which isn't a lot in the grand scheme of things, but it's still more than it should be. So that's why it's important to make sure you blow that stuff off. Make sure you try to keep the area as dust free as you can as you're going from there. I know in a data center that can be kind of difficult with all that blowing air, but do what you can. Fiber connectors need to be cleaned every time they are muted or mated and unmated. Now, to wrap up this video, we have the last term, or last technology is going to be dense wavelength division multiplexing. If you've never heard of that, that's okay. So optical signals of different wavelengths do not interfere with each other on the fiber. Wavelengths used in DWDM are tightly spaced in a 1550 nanometer window. And you have DWDM takes multiple signals, each of which is assigned a distinct wavelength or channel, and injects them onto a single fiber. So it allows you to multiplex the cable so that you're not just dedicated to one individual connection type and forwarding capability. So it gives you a lot of flexibility so that you don't have to sit there and run. You've got 100 different connections you're trying to make. You don't have to run 100 different lines. You can multiplex them in the different ranges and get the traffic across the wire and using just one wire. Very flexible.